We're going to talk about types of aqueous solutions and solubility. So let's think about two familiar aqueous solutions. Remember, aqueous means that it's dissolved in water. Salt water and sugar water. If you put salt in water and stir it up, it looks like it disappears, doesn't it? And the same thing for sugar. Both of these compounds make a homogeneous mixture in water. They don't settle out. They don't have layers floating or anything like oil and water. They mix thoroughly and uniformly, and they form homogeneous mixtures. But what happens when these salts dissolve in water? Not salts, one of them's a salt. What happens when these solids dissolve in water? Well, when a solid is put into a liquid, and by solute we mean the substance that is dissolved in the liquid. Solvent is the thing that the solute is dissolved in. We'll come back to that. There's a competition between attractive forces. The reason that compound was a solid before you stuck it into the solution was that there were forces holding the particles together, whether they were ions or molecules, holding it together. The reason that the solvent is a liquid and not a gas is there are interactions between the molecules. The water molecules are being held together. When we mix these two different compounds, they're compounds. When we put the solute into the solvent, now we also have the potential for interaction between the solvent molecules and the solute molecules. And depending on the relative strengths of all these different interactions, the solid may dissolve or it may not dissolve. It's a little bit like people mixing together. You get two large groups of people. If there is a really strong interaction between these purple people, they may exclude the green people, right? Or if the green people are really attached to each other, they just like each other a lot. It's a little bit like that clique of girls in high school. And you couldn't even get in there to say anything because they were just so tight together. I saw a smile in the back. You've seen this. Mean girls, right? But they're just tight with each other, and they're not going to mix. If the interactions between these purple people are weak, or they're similar to the interactions between the green people, then things are going to mix up. Another way I've done this analogy is, and I can do this, and it's not being racist or anything, because I'm of Swedish descent, and so I'll talk about Swedish immigrants, and my husband is Japanese, so I'll talk about Japanese immigrants, and I'll be safe, right? Nobody will be offended. If you got a group of Japanese immigrants and a bunch of Swedish immigrants together in a same room, if they didn't speak English, would they mingle very well? No, why not? They can't communicate with each other. And the interactions between these particles are a little bit like language with people. If we don't have something in common, we're not going to hang out together. Now, as it happens, almost all Swedish people speak English, and many Japanese speak English as well. So if they have a common language, then they're going to interact and mingle with each other much better than if they have no common language. And so these interactions between, not between I just didn't want to flip the slide there. The interactions here, if they are similar in type and in strength, the solute will dissolve. And if they are different, they will not. Well, you need to talk about these interactions a little bit. Here is a model of a water molecule. The electrons in a molecule of water are not distributed evenly. There is a stronger or a more dense region of electrons over here, and this region of the water molecule are slightly positive. This is not an ionic compound. This lowercase Greek delta means a partial charge. There's a partial negative charge here. Could be a third, a fifth, a seventh, something like that, a fractional charge. And the other end is the same amount of charge, but positive. So because of this, water interacts with ionic compounds because it can speak this charge language that the ions speak. So the negative end of water is attracted to the positive sodium ion from sodium chloride. The positive end of water is attracted to the negative chloride ion. And so I imagine these guys coming up and, oh, hi there, chloride ion. Come out and play with us. And they're being all friendly, nice to it, right? And the same thing over here, but water is showing its negative side to sodium. And so in this way, we have interactions, even though water is a molecular compound, because it's a polar compound, it has this unequal charge distribution, it can interact with the sodium ions. And here, in this illustration, we see the negative sides of water molecules surrounding the positive cation, and that makes this cation comfortable. It replaces the interactions that it had with the salt it was a part of. So this is the positive ion. It was attracted to these negative ions. But now it's surrounded with the water molecules. And the negative ion also becomes surrounded with water molecules, but the water turns its positive side toward it, and this interaction with the water replaces the interaction that it had with the positive ions in the sodium chloride. And so what happens is the ions are able to separate. And the result is we have a homogeneous mixture with sodium chloride ions distributed throughout, and we also have charged particles that are able to conduct electricity. Electricity is the flow of electrons. Water, pure water, does not conduct electricity. But if you put some salt in it, it does conduct electricity because we have these ions that are free to move. Here's an illustration. Of course, looking at the picture isn't nearly as fun as looking at an actual demonstration, but I don't know where they keep these sorts of things, so we'll have to look at the pictures. If you put table salt into water, it will conduct electricity and the light bulb will glow. If you have pure water, it doesn't conduct electricity and the light bulb will not glow. If you pour sugar into the water, the light bulb still doesn't glow. Because sugar does not ionize in water. It doesn't form ions. It's a molecular compound, and there are no charged particles to move the current. So we have these terms, electrolyte and non-electrolyte. An electrolyte is a substance that dissolves in water to form a solution that conducts electricity. And those things that are in Gatorade, right? Why do you drink Gatorade? Because it's got electrolytes in it, and you've been exercising so hard that you're getting dehydrated and you've lost your electrolytes. No, actually, you just taste it. You drink it because it tastes good and you feel more virtuous than drinking Kool-Aid, right? But electrolytes are ionic compounds that are soluble in water. Your body needs sodium and potassium and chloride and a variety of other ions. And so when you sweat, you lose a lot of those ions, and if you lose too many of them, you can get into some serious trouble. So by drinking an electrolyte solution, you're replenishing those electrolytes in your body. Your body does not need all the sugar that's in the Gatorade, but that makes it taste good, because otherwise it tastes like you're drinking salty water, and that's no good. But an electrolyte will conduct electricity. A non-electrolyte does not conduct electricity. So soluble ionic compounds are electrolytes. Most molecular compounds are not. If we look at sugar dissolving in water, because sugar does dissolve in water very nicely, here is a model of a sucrose molecule. And we're using white balls for hydrogen and red for oxygen and black for carbon. And so we see a lot of red and white on this molecule, don't we? Sugar molecules also have some unequal charge distribution, and so there's going to be this attraction between the negative oxygen atoms and the partially positive hydrogen atoms. And so they also speak the same language. And so these sugar molecules will get surrounded by water molecules, and that enables them to float around and make a homogeneous solution. We've talked a little bit about acids. We've learned how to name acids. Acids are molecular compounds, but when we put them in water, they ionize, they form ions. So that can be a little confusing. It's a molecular compound, but it's got ions. It only forms ions when you put it in water. If an acid forms hydrogen cations, and then it forms whatever the anion is. And the hydrogen ion gets pulled off by its attraction for the water molecule. So here we have an illustration of acetic acid. This is the acetate ion, and it's got a hydrogen ion attached to it. When you put it in water, some of the hydrogen ions will get pulled off. You'll have acetate ions, and you will have some acetic acid molecules. A strong acid ionizes completely. So the strong acid, like hydrochloric acid, will dissociate completely into ions. A weak acid will only ionize a little bit. So here's an equation showing acetic acid. It makes some hydrogen ions and some acetate ions, but actually most of it is found as acetic acid, the molecule. We just talked about electrolytes and non-electrolytes. Strong electrolytes, like the strong acids, dissolve completely as ions. So the soluble ionic compounds are strong electrolytes. Strong acids are also strong electrolytes. Strong has nothing to do with how concentrated or how dangerous an acid is. It just has to do with whether it ionizes completely or not. So a strong acid is a strong electrolyte. It will conduct electricity well. A weak electrolyte makes the light bulb glow very weakly. It doesn't conduct very well. A weak acid will allow the solution to conduct electricity, but not very well because it only forms a few ions. So weak electrolytes, weak acids conduct weakly, right? So strong, 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 weak, weak, weak. So this is an illustration of that. Here we have the non-electrolyte. This is something you throw it in the water, light bulb does not go on at all. Something like sugar. There are no ions here. We can't have the flow of electric current without ions, charged particles. This is acetic acid, which dissociates a little bit. So we see some of these, here's one hydrogen ion. I think it came off of this one because there's a little negative sign. So there's one hydrogen ion and one acetate ion, but most of the acetic acid is still the molecule. The molecules don't conduct electricity, only the ions do. So this will cause the light bulb to glow, but just a little bit. Like that's not going to be enough to read by, right? That's a weak, weak glow. And this is a strong electrolyte. Sodium chloride dissolves completely into ions. Sodium ions, chloride ions, lots of them, conducts electricity well. When you dissolve an ionic compound in water, here's an example with sodium sulfide. Ionic compounds will generally dissolve completely, and you get the sodium ions and the sulfide ions, they separate from each other, and we saw that in the illustrations. They get surrounded by the water and they move away from each other. This is called dissociation. Association is when things come together. Dissociation is when they go apart. If your ionic compound has a polyatomic group in it, such as sulfate, the sulfate ion actually stays together as one ion. Because a sulfate ion is sulfur and 4 oxygen atoms that are covalently bonded together. they're not held together by ionic bonds, they're covalent bonds. So we've got the sulfate ion and the sodium ions, and they're going to separate and go their own way. This molecule, or this formula unit, has 2 sodiums and 1 sulfate, and so it will form 2 sodium ions and 1 sulfate ion, and they will go off on their own. So the ionic compound dissolves in water. We've got a solution that contains separated ions. But not all ionic compounds dissolve in water. So if we stay with simple terms, if the compound dissolves, we say it's soluble. And insoluble means it does not dissolve in water. But those are very broad categories. They are qualitative descriptions, not quantitative descriptions. Because even something that's termed insoluble dissolves at least a little bit. If you put a compound, say silver chloride, which is generally considered to be insoluble, if you put it in water, do you think there might be 1 silver ion and 1 chloride ion that might go off into the water? That's certainly possible. So even 1 ion going off means it's dissolving a little bit. So I just want you to understand that even though we say something is insoluble, that doesn't mean that there are no ions. There may be almost no ions. It may not conduct electricity at all, but even an insoluble compound dissolves just a little bit. So sodium, no, that's not sodium, silver nitrate. Silver nitrate is very soluble in water. Dissolves, the ions separate. This solution will conduct electricity. It's a strong electrolyte. Silver chloride, not so much. When you mix the silver chloride in water, it just sits like a lump in the bottom. I mean, it might as well be sand, right? Or glass marbles or something. It just does not dissolve. It just sits there. So how do we know if something is soluble or not? Well, there's a lot of different factors. And there's not really any great explanation. You know, we can look at the periodic table and predict charges of many of the ions, right? And that's great. We learn how to do that, and it applies to all kinds of things. We can't do anything like that with solubility, predicting from the periodic table. And so the way this has been determined is empirically by experiment. You take some stuff. Let's take sodium nitrate and put it in water and stir it. Did it dissolve? Oh, look, it dissolved. Let's take something else. Nope, that didn't dissolve. Okay, that one's insoluble. This one's soluble. And you do that a whole bunch of times. And based on observations, we've come up with some rules that help us predict solubility. So these are the rules. At the top of the table are compounds that are generally soluble. If the compound contains these ions, they are usually soluble. And then on the right side, we list exceptions. So if it contains lithium, sodium, potassium, or ammonium, the compound is soluble. There aren't any exceptions. What do lithium, sodium, and potassium have in common? They're in the same group. They're in group 1. Those are the alkali metals. Alkali metals tend to be soluble. Nitrate and acetate compounds are soluble. No exceptions. Chloride, bromide, and iodide. What do these guys have in common? Halides. When they're an ion, we call them halides. The group is the halogens. So these are the halides. These are generally soluble, except when they get with silver, with mercury 1, or with lead 2, they form an insoluble compound. And sulfate compounds are soluble, except with strontium, barium, lead 2, and silver, or calcium. And those guys then are insoluble. The bottom of the table tells us that these compounds are generally insoluble, hydroxides and sulfides, except if it's with lithium, sodium, potassium, or ammonium, Remember, those guys were soluble with no exceptions. So if you've got hydroxide or sulfide with those, they're going to be soluble. Sulfide with calcium, strontium, or barium is soluble. Hydroxide with calcium, strontium, or barium, slightly soluble. Carbonates and phosphates are generally insoluble, except with that group at the top. So, you need to remember this. And the way you remember it is by using it, right? So you're going to need to predict some solubilities. In today's lab, you're going to need to predict solubilities. So try to do it without looking at the table first, and then look at the table. That's how I finally started to remember it.
So for the exam,
Yeah, I'm not going to give you the table. This is 1A. I give you the table in 3A, but not in 1A. So what should we be able to do? We should be able to look at formulas like this and predict solubility. Nickel sulfide. Okay, so what do? Well, we look at the table. Do we see nickel up here or sulfide? No. Here's sulfide. So sulfide compounds are generally insoluble except, so we need to go over here and see if nickel is any of the exceptions. It's not. So then nickel sulfide is what? Soluble or insoluble? Insoluble. So I'm going to say I for insoluble. How about magnesium phosphate? Here's phosphate down here, and only with the alkali metals and ammonium. So this one's also insoluble. How about lithium carbonate? Soluble. Lithium compounds are soluble. No exceptions. So that's soluble. How about ammonium chloride? Soluble. So you get the idea of how to use the table? Start up here, then go down there if you need to. When you find the ion that you're looking for, check the exceptions.